Well, looks like it's time. Welcome back, folks. So we are now on midterm week. Good news is we don't have a midterms. So we have just a unusual exam schedule where there's going to be 3 exams and a final exam. So next week will be our second exam. I guess you could treat it like a midterm because we'll be essentially halfway through when we get to this exam. So far there's notes provided on exam 2. They're very similar to the notes that you have seen before, except for the table that involved the trigonometric substitutions has been swapped out with a table of certain integrals. These are integrals that folks, whenever you encounter them on exams and homework, but especially exams, you're welcome to take these results for granted. So suppose on exam 2, if you had to find the antiderivative of cotangent, you could just cite this is the result and move forward with the problem and not have to worry about being stuck. Then as usual, there's the trig table and common derivatives and definition of the hyperbolics. Any questions about that exam so far then? Okay, other materials that you'll find on the Moodle website are the sample exam 2 file, which is somewhat similar to the last one, except it's really just a selection of problems. If folks would like a selection of book problems, like on exam 1, I can add that to this file as well. Looks like it's a yes, so probably some odd book problems as well. Okay, I'll add some odd problems to this on a section by section basis, as well as you can use these as various other problems. Then the third thing I'd like to add to here, which is not quite prepared yet because the material is a little bit different from last semester, is I want to add the actual exam 2 that was given last time I taught this course. That way you folks will be able to also see what a real exam situation would look like and kind of test yourself to feel where your level of preparedness is. That exam should be posted over the weekend. But that's where we're at so far. At the way it stands, it looks like 11.3 is going to be knocked off the list, so it'll only go up to 11.2. But by the end of the week, I think is the best time to make that determination. So you should watch for this to be edited. If it's 11.3 is going to be on that list, I'll send everyone an email to notify you so you'll know for sure. If you don't get that email, then assume it's only up to 11.2. So that takes us to our work today. The assignment number 7 is completely posted, which is a little bit unusual. I guess there was a lot of free time this weekend. And we're so far going to cover section 9.5. I felt like a first thing to start with is go back to that problem in 9.3 that we left off on. I guess the better word is got stuck on. But any questions then before we start? Okay, so let's think back what the situation was. We're thinking about an object moving through some kind of medium, whether it's, say, a lake or something else more exotic. For example, they say, think of a boat moving through water. They tell us that force is equal to mass times acceleration and is all equal to some function of velocity. They tell us that the force is proportional to the velocity, so that f of v is equal to negative kv. That allowed us to immediately go to this step and write mass times dv dt. The rate of change of velocity with respect to time is the acceleration, so that's where the dv dt came from. It's equal to negative k times v. So this is the first thing we wrote on the board. We really didn't make a mistake because it was just copying. Then the very next step is to solve this as a separable equation. And the very first step was the very first mistake there. So the first thing we want to do if we want to solve this as a separable equation is everything involving variable v, which is here and here, must be consolidated to the left-hand side. We're told m is the mass of the object, we'll treat it as constant, and we're told straight out that k is a positive constant. So we could go the route of, say, consolidate the constants to the right, move things involving the variable v to the left-hand side. If we do that, we can have, say, divide by v to produce 1 over v dv equals, we'll divide by m, so we'll get negative k divided by m. And we're also treating this as a differential, so not a full derivative or limit of a difference quotient. So we're allowed to multiply both sides by dt. Then that would be the correct very first bona fide step. Any questions to that first step? Okay, the things to check are variable v should be associated with the dv. All of these are constants, so there really is no variable t on the right-hand side. Nonetheless, we can still say there's a t to the power of 0 if you'd like. So everything involving t is on the right-hand side. then the immediate step we take in the world of separable equations is integrate both sides once things are correctly set up. So we know that the antiderivative of 1 over a variable must involve the natural log of the absolute value of that variable. Then, because this is all just one large constant, integrating a constant will produce that constant, negative k divided by m, times the variable we're integrating with respect with. So we get natural log of v is equal to negative k divided by m times t. So we're finally on our way, on the right track. So if we want to solve for v, which is what the first part of the problem says, determine v, we can raise, say, both parts, left and right hand side are going to be exponents with the base e. So we'll convert this to e to the power of natural log, absolute value v, is equal to e to negative kt divided by m. Then we have a cancellation so that the absolute value of v is equal to e negative kt divided by m. So it's looking kind of nasty, but at least we're one step away from solving for v. If you ever reach this situation on an exam or a homework situation with absolute value, we can solve by saying v is then equal to plus or minus, oh, we might have made a mistake. Yes, we have made a mistake. Anyone see what the mistake is so far? Very, very critical mistake.
You put natural log on the other side?
Well, we didn't quite have to because this was just a variable t. But there's still one other thing. You're on the right track. From here to here is a mistake. Let's put that in red. We need a constant of integration, correct. If it was, say, in chapter 7, it's not as big of a deal. It was something like a half a point on an exam. But in the world of differential equations, this is really, really critical. That constant of integration must be inserted immediately. Then when we raised both sides to consider them a base or a power of base e, that constant should have copied here. And so now it is over here. If we just threw on a constant by adding, we would have a different form of the differential equation, because this can be re-expressed as plus or minus e to that constant times e to the negative kt divided by m. So that's the solution for v so far. Any questions to that step? Okay, so watch out for that constant of integration. It would be worth a whole serious 1 point possibly on a real exam because it is more important in the context of solving differential equations. Next thing we'd like to know is, what is this constant? Plus or minus e to the power of c. But they tell us the initial condition here is that the velocity at time 0 is v naught. So we're not sure what that initial velocity is, but at least we can use that as an initial condition to solve for this arbitrary constant. So v at 0 equals v naught means that the velocity itself is that initial velocity v naught when time is set to 0, so at the very beginning. So if we go back to this equation here, we can say v is equal to v naught when time, the variable t, is set to 0, gives us v naught equals plus or minus e to the power of c times e to the power of 0 altogether. So the 0 here is really a great convenience factor here because this cancels out. E to the power of 0 is 1, and we know right away that this entire nasty looking constant is just the initial velocity. We can now conclude that v at time t, you could just call it v if you like, or call it v at t to highlight the fact that velocity depends on time, is equal to v naught e to the power of negative kt divided by m. So that would be the velocity of this object moving through some kind of medium at any time t. So we've done the first part, we've determined v, and used the initial condition. Any questions to that step so far? Okay, so this is about what an application might look like if we pick an application for exam 2. Typically, you'll be thrown to really this spot right here, and it'll feel like solving a different separable differential equation, much like the homework. Just be careful of things like keeping the right variable to the right spot and inserting the constant at the right point. But the next part, this is starting to get a little bit long for an exam problem, but a decent homework problem. says also determine s at any time t. So I guess you could say we're halfway done. Anyone see how you would get s from this point so far? One thing we have to say is to get to at s, s is just the position of this particle at any time t. And if we say s of t is the displacement or position then we can also write that the rate of change of the position with respect to time is what we mean by velocity. So that's how we would define velocity, and that's why this problem has all sorts of symbols going on. It's trying to remind us that the second derivative of position with respect to time is velocity, and the bit that's missing there is the first derivative of the position function with respect to time is velocity itself. So this is a nice equation because we can immediately take this and say, therefore, s of t must be the antiderivative of v at t with respect to time. So in other words, if s is equal to, if the rate of change of s is equal to velocity, then the antiderivative of velocity must be the position function. So we have to take v at t, all of this stuff right here, and find its antiderivative, which is really not too bad. I mean, it's turning into a mess of constants, but at its heart, it's the antiderivative of an exponential function. Things that could go really, really wrong with this is if it was to a power 2, then we would be forced to invoke the fundamental theorem of calculus. But if it's to the power 1, we can do that integral. So let's write it out and say s at t is now the antiderivative of v naught, which is constant, the initial velocity, e to the power of negative kt divided by m dt. So we're one antiderivative away of getting the position function, s. S of t is now equal to, first we take the antiderivative of this. Let's copy the v naught lest we forget it. Antiderivative is e to the negative kt divided by m. I wrote it in a slightly different way to emphasize the constant, because we know by chain rule this will never check as totally accurate. So we take this coefficient, invert it, so I have a negative m divided by k. And now if I take that whole form and check with the chain rule, I would take the derivative of base e, it produces this with the same exponent. We multiply by the derivative of the exponent, which is negative k divided by m. It would multiply and cancel with the negative m divided by k. So now we have s of t, but don't forget, immediately at this step we need a new constant. Let's call it, say, maybe a c1, so that we don't get it mixed up with this constant c from before. So we have s of t. We need to use the initial condition that s at time 0 is s naught, and we'll have to determine the constant c1. Any questions to that step? Okay, so we're really redoing this whole bit right here. If we're told that this is the function s of t, and s of 0 is s naught, then s naught can be put at the left-hand side. 0 is the value of the variable t, which we're going to insert right there. But as soon as you put a 0 there, this whole thing turns into e to the power of 0, which is 1. And all we get is all the constants. So v naught, let's make this negative v naught times m divided by k plus c1. So therefore, we now know that c1 is equal to positive v naught times m divided by k plus s naught by adding this to both sides of the previous equation. So it's turning into lots and lots of constants, but it is what it is. I think probably the nastiest thing about this problem is the bookkeeping of carrying every single symbol that really isn't doing much but requires copying. So next we can say finally, after determining the value of c1, s of t is equal to, now it's v naught, let's write this, negative v naught m divided by k, all that stuff there. The exponential portion is e to the negative k divided by m t. Then we'll add c1, which is plus v naught m divided by k plus the initial starting position at time 0, s naught. So that's the solution to the position at any time t. So if you run an experiment that models some of these kinds of processes, the challenging thing is to determine the constant k that they gave us. That could take some experimental work in the lab. But once you have that constant k, you can come up with an approximation of what will happen to your boat moving through water as their prototypical example. This is where it'll be at any time t. Any questions to that point so far?
I guess I got a question.
Yeah.
So when we were doing the, when you did the antiderivative, why did you not have the t?
Right here?
Yeah.
Gotcha.
Why did you not have the t times by the k in the next step?
Right down here?
Yeah.
Well, it kind of is. It just depends on how it's presented. I wrote it as negative km times t like this, but you could have also rewritten it as negative k times t divided by m in that way.
So why was it not negative m over kte?
Or you mean the flipped version inside here?
The reciprocal of it, yeah. So why do we not have the t there?
The t down in here,
Yeah.
you're saying?
Yeah.
Oh, I gotcha. If you did have a t down in there, say negative mk times t e to the negative km times t, the trouble is the derivative of this whole thing must be exactly the integrand for this to be the correct antiderivative.
Oh, okay.
But once we check this out, this is our problem right here. It's going to involve a product rule, which will come as two different terms. The very first term would be equal to this, but then it would be, for the second term, t times the derivative of this, which would change the constant out here.
Okay.
Other questions about that so far? Okay, that takes us to the last step. If we know that the velocity at any time t, and if we are further able to find out the exact position of this particle at any time t, then by any rights, we should be able to find out the total distance this object is going to travel from starting time t is equal to 0. So the way this is going to work is, we're going to imagine that as time proceeds, this object is going to get closer and closer to some point, but as it gets closer to that point, the force resisting its movement is also increasing. It's going to reach some equilibrium point where it's just going to approach infinitely close forever. So we can have a notion of what its total distance might be as time goes off to infinity. So that we can say the total distance, you'll never really realize this total distance. So it's kind of an abstract problem in reality. We'll say the total distance is in fact the limit as t goes to infinity. Well, time can in fact go to infinity, we might say. Depends on what the physicists are telling us these days. But if we let time run off to infinity of s of t, that ought to be the total distance, right? It's actually very close, but there's one little factor we're off by. If we took this limit, we have to also account for the initial position of s naught. If that initial position of s naught was 0, this would be the correct thing. Because it's not 0, at time t equals 0, say s of 0, this would become a power of 1. This and this would cancel to 0. We're getting an s naught. So we didn't actually travel that distance of s naught. That's just where we started. So we have to go minus s naught to get the right distance. Now we take the limit. So the limit as t goes to infinity is for this entire function. It's a huge mess, but it is what it is. That's just what happens in physics, I suppose. So we take the limit as t goes to infinity of negative v naught m divided by k, e to the negative k divided by m times t, plus v naught m divided by k, plus s naught, minus s naught will allow those initial positions to cancel, so we don't get any free distance out. Then we need to know what the graph of this looks like. If we do, then we'll be able to compute the limit. That graph could either look like this, the exponential that is increasing forever, or it could look like this, the exponential that is decreasing forever. If it's the exponential that's decreasing forever, that limit of this would be 0. If it's increasing forever, the limit would be infinity, and we could say the total distance is in fact infinity, which is a strange thing to say. It would mean the problem is essentially ill-posed. So which version would you say it is? The increasing exponential or the exponential decay graph?
Probably the negative, right? Because k is
Exactly, yeah. It ought to be this due to the negative here. They told us that the constant k was positive, so that's helpful too. If they told us the constant k was negative, then this would have been positive altogether. And m was the initial mass of the object. That ought to be a positive quantity as well. So this entire quantity, negative k divided by m, is negative. So that takes us to that curve, which is always decreasing. Which means in the limit, this whole chunk goes to 0. This is now equal to v naught m divided by k plus s naught minus s naught, which is equal to v naught times m divided by k. So if this was the process that you're modeling, that saying that that's the total distance, well, in practice, that's just a distance that your object would never actually exceed until the heat death of the universe. Time has to go off to infinity. So at least we would have an upper bound on what its actual distance would be if we stopped the experiment at any possible time. But that's the solution to this weird problem. I would say that going from here to here and getting to this step is probably the most important features. But it's nice to see what all interesting kinds of things differential equations can solve, rather than just ripping from method to method. Any questions then with this problem so far? Okay, so that takes us to the separable equations method. Off next to is the first order linear equations, section 9.5, which is the first topic on the homework. And we'll talk a little bit about this hint in the homework as we get through it. So we're now in section 9.5. So it feels like we're changing gears, but really it's still differential equations. We just have a different format of the type of equations we're getting. So this is called first order. This tells us that there's only a first derivative at highest, and the equations we'll see. Linear, defining it as linear takes a bit of work. So we'll talk about what a first order linear differential equation really looks like. But to really get at that, a proper course in differential equations is probably more helpful. But this will be first order linear differential equations. I'll start off with the definition that says any differential equation that can be put in the form which is y prime plus p of x. Think of it as f of x, just some function times y equals another function q of x. So these are going to be the objects which we'll study. The solution will be some function y such that if we take its derivative, a function p of x times the same function, it must be equal to some other q of x function we've specified. So any differential equation in this form is called a first order linear differential equation. And again, the linear here is a pretty weird word. If you're taking linear algebra and then you take differential equations, it'll be a little bit more clear. But it is linear in the sense of linear functions and linear algebra. So I think it's worth mentioning that for folks taking that course. So that's what the equations look like. And the book spends about maybe 2 pages deriving this result. Because it's not a differential equations course, let's just take this result as for granted. The solution to this equation can be found by multiplying both sides by the integrating factor, and that's just a whole other definition. So this is really the punchline to solving this thing. The integrating factor, we call it I because of integrating, it depends on the variable in the problem. So we remind ourselves it's a function by writing I of x. It's defined to be the base e exponential to the power of the antiderivative of the p of x function, dx. So we need to take that, integrate, get e to whatever the power is, multiply it on both sides, then we can solve the equation, but we have to specify how it's solved. But that is the main ingredient. And if this was, say, an exam 2 problem, I would say the integrating factor is probably at most half the credit of the entire problem, since in many problems it's a requirement. However, as the hint says in the homework, you should look at your differential equations very, very carefully before you proceed to solve, since many of them in the homework do not need an integrating factor, and that's a possibility on the exam as well. So that's the setup. Next thing we need to do is look at some examples. Any questions first before we see what we're getting into? Oh, let's start off one then where we do need an integrating factor. We'll look at one where we do not need one so that we can compare what is required when. So this is a very typical kind of equation you might see. This goes e to the x times y prime plus 2e to the x times y is equal to 1. And instructions for all of these are to solve the equation. Okay, so that's the thing we'd like to solve. One check that we should always do here is analyze the e to the x. The derivative of e to the x is itself, and if the 2 was gone, it means we would not have needed an integrating factor. We could have just immediately begin to solve this equation. So if it had looked like this, the work would have been cut in half essentially. That 2 is throwing everything off. So we're going to start by using the integrating factor. So this is our step 1 in this problem. I of x will be e to the power of something. What would you say that something ought to be? This is a really nasty step 1. Because what's nasty about this step 1 is the integrating factor here is referring to this equation where the leading coefficient is set to 1. So the integrating factor is in fact 2. Does that make sense to folks? We really need to get to this form where y prime is isolated. So we're looking at, as soon as we divide by e to the x, y prime plus 2y equals 1 over e to the x, or e to the power of negative x if you prefer. So this is our p of x function here. So step 1 is to derive the integrating factor, antiderivative of p to the x dx, but that would just be 2 in this problem, whatever the coefficient of y without the prime. So 2 dx. Antiderivative of 2 is just x, so we obtain e to the x. Another very common question about this is there is many possible integrating factors, right? We can add an arbitrary constant of integration, for example, and come up with infinitely many different kinds. All of them can solve the differential equation, so we pick the simplest one in this context. So when we're finding the integrating factor, we do not, or let's say here, use the simplest antiderivative. So that e to the x is essentially the key to the whole problem, or e to the, 2x, forgot the 2 there. So if we multiply both sides by e to the 2x, we'll be able to solve this problem. Any questions to this step so far? Okay, so step 2 really is using this information right here, multiply both sides by the integrating factor is our second step. So we'll take e to the 2x times y prime plus 2 e to the 2x times y. E to the 2x times e to the negative x is just going to give us ordinary e to the x on the right-hand side. So we're on our way. And every time you look at this, whether you're looking at the very first line of the differential equation or whether you're on this step and just determining if you're on the right track, what we're trying to get is that if we took the derivative of this, d dx, we had better get 2e to the 2x. Do you folks believe that ought to be the case? So I'm saying yay? Yeah, the derivative of e to the 2x involves itself. The chain rule will force us to multiply by the derivative of 2x, which produces that 2. So if we have that the derivative of this is equal to this, then another thing that's suspicious is looking at y. The derivative of y is also right here. We're really looking at a chain rule at this step, and step 3 is to reverse that chain rule. Step 3, undo, not the chain rule, excuse me, the product rule on the left-hand side. LHS for left-hand side. So let's do just that. We can write here, there's a function, e to the 2x, and there's another function, y. We can put a prime on it or a d dx if you like. If we check this carefully by the product rule, you could say, depending on your favorite order of the product rule, take the derivative of one function. I'll do derivative of y, do y prime, and copy the other. That's precisely what we have as the first term. Then you go plus, take the derivative of the other function and copy the one you derived first. So there's the copy. Derivative of e to the 2x would in fact go there. So if you worked out the product rule, the previous line is precisely that. The right-hand side is an ordinary e to the x. If we want to solve this equation, step 4 is just integrate both sides. And that's going to be the process on essentially every single one of these linear differential equations, where in some of them you can entirely skip the integrating factor step if we look really carefully. So we'll say for step 4, integrate both sides. So that means we're slapping on an antiderivative symbol with respect to the variable x on both sides. So it's two antiderivative problems that we have to solve simultaneously. So I'll go first. Antiderivative of e to the x is itself plus, don't forget, constant right at that step. What would you say the antiderivative of the left-hand side should be? It's kind of tricky, right? Because if we did that antiderivative normally, you might say, well, find the derivative of this first, working inside out. Then you'd be taking the antiderivative of all this stuff. But that's just a humongous mess, and it's not entirely possible until you know what y and y prime itself are. That's the whole purpose of the problem, right? To determine y, so you would know what y prime is as well. But if you look at this carefully, it's saying, find the antiderivative of the derivative of this stuff. Would you folks agree it ought to just be that stuff, e to the 2xy? We're just taking a full antiderivative of a derivative itself, so there's an immediate cancellation. There would be our constant of integration, but we're visualizing this as all constants absorbed into one overall constant on the right-hand side. Let's take a look at a shortcut, however. If you are confident that all of this is correct, notice that I have essentially taken this whole thing, carried it down, and dropped the y prime. That would happen at every single time you do one of these types of problems. So that's another really nice feature about these. In some ways, they're a little bit more straightforward than separable equations, because with separable equations, you have to wrestle around with how can it factor with variables to one side, variables to the other side, and that's not always completely straightforward. So remember, we're solving for the differential equations, which implies we want to have an explicit solution. If you're solving a first-order linear differential equations, that's always something you can get. So there's nothing in this homework set that says, say compared to the last set, 5 and 7 should be left in implicit form. So every problem in 9.5 can be solved for y. It's just a matter of dividing by whatever the integrating factor happened to be, e to the 2x in this problem. So we'll do that as our ultimate or final step. Y is now equal to, for dividing e to the 2x to both sides, there's loads of algebraically equivalent ways you can write this. If you just left it in that form, that'd be perfectly fine. If I was to imagine or try to guess what the book would write, they might write it this way. Y is equal to e to the negative x plus a constant times e to the negative 2x. And either form is completely acceptable. Any questions with that solution so far, and in either form? Okay, so that's the method of solving first order linear equations via integrating factor. But again, the most important thing about these kind of problems is first deciding if it is a first order linear equation, and second deciding if you really need an integrating factor. So let's do a problem immediately where an integrating factor is not necessary, and also explain why. That ought to be really important as well. So same instructions, it's just find the general solution to the differential equation, or solve the equation for short. And this one reads x cubed y prime plus 3x squared y equals hyperbolic cosine of x, for no particular reason other than we don't seem to deal with those very often, so we threw it in. So that's our whole problem. And you can copy the exact method on this problem if you like. You could divide both sides by x cubed. Notice that's going to insist that x is bigger than 0 if you did that. Was there further things that insisted that? No, it should say x is bigger than 0 here. So that when you divide by x cubed, you're not in fact dividing by 0 at all. And if you did that and found the integrating factor, you would find that you're now going to multiply both sides by x cubed, and you would end up exactly back at this step. It's extremely frustrating. So the thing that to look for in every equation of this form is x cubed here versus this is really special because this is the derivative of x cubed there, 3x squared. Whenever that happens, you do not in fact need an integrating factor. It fails over here. This was not equal to the derivative, so we actually had to insert the correct thing, or here to here rather. This e to the x is not equal to 2 to the x in the derivative, and that's why we had to do essentially twice the work. First finding the integrating factor, then reversing the product rule. So here we can immediately say that this is the same as x cubed y prime equals, to give us a little bit of space, hyperbolic cosine of x, and take the antiderivative of both sides. But again, the logic of this is, if I were to find the derivative of x cubed times y, I would probably, just to keep the order the same up here, take the derivative of y, and there it is, copy x cubed. The next step would be copy y, and there it is, and the derivative of x cubed would give us the 3x squared. So immediately, the product rule is reversible on step 1, which means we can write x cubed y prime, take its antiderivative with respect to x, it'll be equal to the antiderivative of hyperbolic cosine with respect to x, and now we're well on our way. So the antiderivative cancels with the derivative, and we just get x cubed y on the left-hand side. And again, this is a decent shortcut that you're welcome to take. If you know that you're already set up and you do not need an integrating factor, you can drop from this step immediately to this step by copying the function x cubed, copying y without the derivative, and that's how they all resolve. I like this middle step because for me, this is the logical glue that tells me how all of that turns into just that. We undid a product rule. But I'll keep this as optional work. Antiderivative of hyperbolic cosine is hyperbolic sine, and now the all-important constant must be inserted immediately at that step. So we're one step away from solving the equation. Any questions to that step? Okay, so this problem is really quite short. If you just went from here to here, that would be one step. Final step is divide by x cubed, and y would be equal to hyperbolic sine of x plus a constant, divide by x cubed. And there we've done it. We've solved 2 linear differential equations, and probably the time it may have taken us to solve 1 moderate difficulty separable equation. So these are easier, which means it feels like the book is misordered in a weird way. The reason 9.5 comes well after 9.3 is that the book wants to prove that this is the method that will always work in going from here all the way to here. To do that, they in fact have to solve a separable equation. So our method of first order linear differential equations is something that is derivable by using separable equations itself. And that's why our textbook is ordered sometimes harder problems and then easier problems. Just the way it is. They like to prove everything. But questions so far with these couple problems? Okay, one question you might have is, how can we tell whether or not our linear equation can be solved by separating? In other words, are some linear equations separable? And the answer is, yes, some of them are, but not all of them. So one thing to look out for are equations that might look something along these lines, for example. If you have, say, maybe something along the lines of x plus y dy dx equals 0, then this would be considered separable. So this is separable. Whereas if you write something along the lines of maybe x dy dx plus y equals a 1, this is non-separable. So the first one is an ordinary separable equation. This is not linear, and the not linear portion is due to the y dy. It just doesn't have the form of doing a y prime plus a p of x, y equals a q of x. So for an equation like this, it would be mandatory to solve it using the separable method. If you take a function times its derivative, and we're solving for that function, then we're square in the separable end. This one, however, is non-separable. Anyone see why this one would be non-separable versus this one? Or is it separable? Maybe let's just throw in some extra good stuff in there to mess it up. How about that? Now it's really kind of all messed up. In order to get this to separate, you would have to try to solve for, say, dy dx. Take this x, the e to the xy, and the 1, move it all to the opposite side, and try to factor things involving just x and just y. But there's too much going on there for that to work. It's not separable, but it is a first order linear equation. So those are two examples to try to highlight the differences between the two. If your folks would like, we could try to solve each of them just for the sake of practice, or we could move on to a different problem. What sounds fun to folks? Different problem or try to solve these things? Solve them? Okay, let's give it a try. So we said that this is separable but not linear. If it's separable, we should put our money where our mouth is and separate it. So let's give that a try. If we can separate the equation, then we'll know the method for solving it. So if I were to solve this thing, probably the first thing I would do is maybe subtract x from both sides. So this equation would become y dy dx is equal to negative x. And really all you need to separate the equation is to have variables y entirely on the left-hand side, variables x is entirely on the right-hand side, and that's precisely what we have. So our next step, it would be to write y dy equals, we're visualizing this as a differential, so that would be two different variables altogether, dx being independent and dy being the dependent variable. So we can multiply dx to both sides to get that form. So we've done it, the equation is entirely separable. As soon as you have separated the equation, we immediately integrate both sides with respect to whatever the differential portion tells us to. So this side would be y squared equals negative x squared, let's not forget our divide by 2's, plus a constant. So we've done it. That would be the solution in implicit form. For this, we could go a little bit further and solve for y. But notice that when we do solve for y, we're going to get y squared is equal to, we're multiplying both sides by 2, so this will be just a negative x squared. And you can write a 2 times c1, or 2 times c, but typically what you'll see is just a c1, since if that's an arbitrary constant, double that constant is also some arbitrary constant. And this just causes the algebra to be a little bit simpler if there were further steps in this problem. But one thing you should write as a best practice is to say where c1 actually came from. Just good bookkeeping, and some people require it. Next thing we could do is take the square root of both sides. So y would be equal to either positive or minus the square root of negative x squared plus that constant c1. So that would be our solution to that step. That constant c1 is going to have lots of effects on the domain of this function. And for some constant c1, this function wouldn't exist as a function of a real variable, since this would become a negative root. Also, we have two possibilities, since there's no initial condition to tell us which branch to pick, the positive or negative root. But nonetheless, for a completely made up problem, that one didn't go too bad. This one, however, this one could be nightmare fuel, but let's give it a try. Any questions first? Okay, let's see how far we get, and if we decide that was a horrible made up problem, we can certainly exchange it for another one. So if we were going to try to solve that one, first thing you might try is try to separate that equation. But if you were to try to do that, you would get something along the lines of x dy dx is equal to 1. Let's go, how about, let's keep the, well, there's not a whole lot you can do here. We want to keep the variable y on the left-hand side. The variable x is also on the left-hand side. So maybe as our first step, let's divide by x. So we're trying to separate the second equation, just as an explanation of why you can't. So let's just put here for notes, is equation 2 separable really? So we're going to divide both sides by x, would become dy dx plus e to the x divided by x equals 1 over x. So I'm going to try to get everything involving x to one side. I guess the one thing you could do is, as a next step, do dy dx is equal to 1 over x minus e to the x divided by x times y. So it's so far so good, right? All the variable x is on the right-hand side, and we can move dx over whenever we would like to. The trouble is, y has to be on the left-hand side, correct? The only way to make that happen is divide by y. But dividing by y produces it over here. It's as if x and y are completely married together in this situation. There's just no way to separate this. So I would say for notes, we must divide by y, but that produces a term 1 over xy on the right-hand side, RHS for right-hand side. That means we just can't separate this, no matter how hard we try. There's no possible factorization in this situation. So that tells us this is not separable. But that's okay. It still has the format of a first-order linear differential equation, which we can attempt to solve by our method from before. So let's solve it nonetheless. Let me recopy the equation. I suppose it is right over there. X dy dx is equal to e to the xy. The e to the x, I guess that was just for fun. That wasn't really a mandatory feature of the problem, but there it is. So the first thing I would check is the derivative of x equal to e to the x? The answer is no, so we must have an integrating factor to resolve this. Nonetheless, we are still going to divide by x just to get to the right form. So I'll take this, write it as y prime for the dy dx. We're also dividing by x at the same time to get e to the x divided by x, which is looking really quite bad, times y equals 1 over x. So now it has the form of the first order linear differential equation, and to solve this, step 1 is to produce the integrating factor I of x and multiply both sides of the equation by that factor. But that means we have to solve e to the power of the antiderivative of e to the x divided by x dx, and that's really no fun. That is a horrible made-up problem. Probably a good stopping point because that integral would be impossible to write in closed form, much like e to the x squared. If it was x e to the x, it would be no problem. Integration by parts would do the job. But we're getting stuck a lot on our integrals where if we really want an antiderivative there, we'd have to invoke the fundamental theorem of calculus, which is going to make this problem essentially blow up into a huge mess. So probably a good stopping point if everyone's in agreement. Does that seem all right to folks? Okay, so it can be done, but this one's going to require a tremendous amount of work, just because it's going to involve trying to integrate something that does not have a closed form solution. That's really the whole purpose of Chapter 11, to get a better answer that doesn't involve the fundamental theorem of calculus. But before we get there, let's practice a couple more of these problems and maybe look at an application next class. Does that sound all right to folks? Okay, let's try a couple more typical problems. Next class, we'll look at what are the common applications for first order linear. And then we're going to move over to Chapter 11. So this problem says to solve the initial value problem, and that initial value problem goes y prime equals pi times y plus e to the power of 2 pi x, where the initial value is that we're seeking the one specific solution that passes through the point 0, 0. In other words, satisfies y of 0 is equal to 0. So this is our problem, and we're trying to get our equation into this format to start. So the strategy here is, if we want to solve first order linear differential equation, put it in the format of a first order linear differential equation. It should have the derivative come first. The next term should be the function itself with whatever is attached to it. So here we have the constant function pi times y is equal to, there can be anything at all on the right-hand side. It could even be 0. But if that was the case, it would have been a separable equation, and you might solve it that route a little bit faster in this situation. So now we have it in the right format. Our function p of x here is now pi. So this is the p of x function, negative pi. And that makes a world of difference. The format insists that there's a plus there, so any negative sign must be absorbed into the p of x function. So that tells us the integrating factor, I of x, is e to the power of the antiderivative of negative pi dx. So that's how will be our very next step. Then pi is a constant, so this will become e to the power of negative pi x. Does that look all right to that step, folks? Okay, then we take e to the power negative pi x, multiply both sides of the equation, so it looks like a mess at the moment. E to the power of negative pi x times y prime minus pi times e to the power of negative pi x times ordinary function y equals e to the 2 pi x, e to the power of negative pi x, or just write e to the pi x all together in one step, and that'd be just fine. So that's our equation as it stands now. And there is an important check to do here. This is a check you should do at the very onset, once you have it in this form of the first order equation. But the derivative of the constant 1 is not negative pi, so we use the integrating factor and check that the derivative of e to the negative pi x d dx is in fact negative pi e to the negative pi x through the chain rule. That tells us there is a specific product rule that got us to this step. And we mentioned there's also a specific shortcut to power on to the immediate next step. If you wrote this, where all I've done is consolidate that by the exponent laws, then that would be just fine. You have written the product rule and taken an antiderivative all in one step. But don't forget, if you take the antiderivative on one side, you must do it to the other. So that very next step should be the antiderivative of e to the pi x. So that's a decent shortcut if you like. Any questions to that step via shortcut? Okay, then we need to solve antiderivative of e negative pi x. So e to the negative pi x times y is equal to e to the pi x. With chain rule considerations, we have to multiply by 1 over pi. At this step, we've solved all antiderivatives, so I'd write the constant of integration c at that step. So now we can solve for y if we like, or use the initial condition to solve for the constant if you like. Really, it's up to your preference. But usually, sometimes it's a little bit faster to take this, use the information here to solve for that constant c. So let's go ahead and just solve for it immediately. That way we're not forgetting as well. But first, any questions to this step? Okay, so nearly there. When we look at y at 0 is equal to 0, we're essentially saying when x is 0, y is equal to 0, or we're really also just saying the curve we're producing goes to the point 0, 0. So if we do that, we're throwing in 0 for y. The entire left-hand side has just been wiped out. So we get 0 is equal to 0 for x. Gets inserted here, but that becomes a factor of 1 times 1 over pi. So we get 1 over pi plus a constant. So that means that constant of integration c is equal to negative 1 over pi. So we'll insert that here. Also, we can say divide by e to the negative pi x, or multiply by e to the positive pi x at the same time. If we went that route, e to the positive pi x, on both sides of the equation, then our solution would be y equals, due to the cancellation here, e to the pi x times e to the pi x over here gives us 1 over pi e to the 2 pi x, and our constant c was negative 1 over pi. So visualize this c as minus 1 over pi times e to the pi x. And finally, that would be the solution to that initial value problem. Any questions with that problem so far? Things you could do is, if you really have extra time, you can take this function here, find its derivative, see what that comes out to, and just algebraically work out pi times y plus e to the 2 pi x, see if it's actually equal to the derivative of that function y. That's decent stuff to do. It's not mandatory on homework or exams, but notice when we were in section 9.1, way back in the day, that was the key problems that we were looking at. So that will be an exam 2 problem in its own right. I'll give you a differential equation, maybe something like this. I'll give no steps on how to solve it. I'll just say, is this or is this not a solution? So that's a good problem to always be ready to go with. Should we give that a try just for the practice? Okay, so as a bona fide problem in its own right, let's call this, in part A, solve the initial value problem. For a whole nother problem, part B, let's check the solution. And part B would just be one single problem exam. I wouldn't make you do both on one problem. That's quite a lot of work. So it'd be worded in about this way for a part B. Check if y equals, and I forgot what it was, 1 over pi e to the 2 pi x minus 1 over pi e to the power of pi x. Check if that is a solution. We cannot any longer say the solution because there's infinitely many of them. We want to check if it is a solution to, not the full initial value problem, let's just take the differential equation itself. If we want to check if it's a solution to the initial value problem as well, you just have to insert 0 and see if you've got 0 as well. Yeah, if you put in 0 here, that would become a 1. That would become a 1. It'd be 1 over pi minus 1 over pi. So that would satisfy the initial condition. But we're focusing more on this. So if I were to work out this problem, first thing I would do is go here and just calculate its derivative. So let's take y prime. We're first going to use the constant rule, so it'll be 1 over pi times derivative of e to the 2 pi x. So we throw in e to the 2 pi x. Chain rule says multiply that by the derivative of 2 pi x, which is a 2 pi. So I'll insert it in front where that space was, and then just rinse and repeat. So we'll have minus 1 over pi multiplied by the derivative of e to the pi x, which is itself, times pi through the chain rule. So that's the derivative. Once we simplify this, we have that y prime would be 2 e to the 2 pi x. Cancellation here to here would be minus e to the pi x. So that's the left-hand side of this equation. Now we work out the right-hand side and see if they match. If there's a mismatch, then that half of the chalkboard is incorrect. And we will have to dig out where the error has to be. But questions to that first portion of the problem? Okay, next, we're just focusing on this. Pi y plus e to the 2 pi x. So pi y plus e to the 2 pi x would become pi times, we have the function y here, so we do a substitution as our next step. So we're taking pi times 1 over pi e to the 2 pi x minus 1 over pi e to the pi x, and there is y in its full glory, plus e to the 2 pi x. And I think I wrote that x in a very weird way. That's an exponent, so it should be written in that way. So we'll just do a bit of algebra, see what we get. It's bad luck to look over there, so I'm just going to focus over here for now. Pi is going to wipe out the reciprocal of pi to give us e to the 2 pi x minus e to the pi x plus e to the 2 pi x. So these and these would be the like terms in the problem. So we can say we have 2 copies of e to the 2 pi x minus e to the pi x. Then we have 2 e to the 2 pi x minus pi x, or excuse me, minus e to the pi x. So that's both sides of the differential equation. The left-hand side satisfies this is the derivative. The right-hand side is exactly equal to this quantity. So we can say for our assertion, this shows y equals 1 over pi e to the 2 pi x minus 1 over pi e to the pi x is a solution. By a solution, we mean a solution to this differential equation. That's not a horrible amount of work for a check, but it does take about the same amount of time to do the actual differential equation itself. So I feel like that would be an entire problem in its own right on exam 2. Does that make sense for the logic on how to check whether or not a supposed answer is in fact a bona fide solution?
I just got one question.
Yeah, you
So,
bet.
how did you set up the second part of it? I guess I just missed it. Like, where did you get the pi?
This pi right here?
Yeah, like where did you just get that whole thing from?
Oh, the pi y e to the 2 pi x, this came from the original differential equation itself.
Okay,
So I took this as the original differential equation and just started substituting in the supposed answer of y into y there. So whatever the right-hand side was, I just copied it immediately up here. And the substitution came from this, all of that stuff there. Does that make sense for that substitution here and where the pi came from? Awesome. Other questions about that problem? Okay, I think we have just enough time for maybe one quick problem. Does that sound all right to folks? We'll do one quick problem, maybe a warm-up problem when we come back. If people are feeling like it, we can do another interesting application as well. But for one last problem, let's see, we've got something like, we go to 807. Let's take a look at maybe x natural log x, y prime, plus natural log of x plus 1 y equals x e to the negative 3x, and that's our problem. So we want to solve that problem there. Step 1, it would say, divide by x natural log x into all sides of the equation, form the integrating factor. Remember, you really want to take your time with this and look at this carefully. If you look at x natural log x natural log x, and the derivative by the product rule would be the derivative of x. So I copy natural log x plus take x, multiply by the derivative of natural log x, which would be 1 over x. It would come out as natural log x plus 1, which is precisely what is here. That tells us we can entirely skip the integrating factor step and write that this is the same as x natural log x times y prime equals x e to the negative 3x. So that could be our immediate first step to this problem. Does that make sense to that step? Notice that this could be a really, really horrific problem. If you did, in fact, divide by x natural log x here, work out all the algebra very, very carefully, this problem is going to be very, very enormous and possibly untractable. So identifying that this works out, that the product rule can be reversed in one single step, massively reduces the work. We still have to find this as an antiderivative. That's an integration by parts with u as x, dv is e to the negative 3x, dx, so that du is dx, and v is negative 1/3 e to the negative 3x. So that table will support us ripping through this as an antiderivative, just in case we run out of time since we have like a minute and a half. But the antiderivative of the left-hand side is immediately an x natural log x times y, which is now equal to, let's form the integration by parts on this right-hand side. It'll be u times v, so negative 1/3 x e to the negative 3x, minus the integral of v du, which is negative 1/3 e to the negative 3x dx. So that would be our next step after going through integration by parts. Does that look all right to that step? Then we've got something like 20 seconds. Let's see how far we get. There's x natural log x times y equals negative 1/3 x e to the negative 3x. This we can consider positive, and the antiderivative of e to the negative 3x is itself, but we have to divide by negative 1/3 and multiply it by positive 1/3, so it's a negative 1/9 plus a constant. Then the whole problem is now solved as soon as you divide by x natural log x. So the solution y is a huge mess, but let's just write it this way. 1 over x natural log x, there we divide by it, and copy everything else. Minus 1/3 x e to the negative 3x, minus 1/9 e to the negative 3x, plus a constant. And there doesn't really appear to be a meaningful way that simplifies, so it's just fine to leave your answer in a form like that. Any questions about that problem? Okay, we'll look at a couple more problems next time, go a little bit slower than that one, and we'll start chapter 11 as well. If there are any questions, feel free to stick around. And drive safely. No telling when that stuff's going to turn into a skating rink.